Greetings! This video is a quick review of logic circuits. I'm Yousefzadeh. We will cover Boolean algebra, logic gates, logic minimization, combinational and sequential circuits. This video is recommended for those who want to review logic circuits in a concise and quick way. It's not recommended for those who are learning logic circuits for the first time. So let's get started. Boolean algebra is a branch of algebra in which the values of variables are true and false, 1 and 0. Main operations are and or not. Sometimes they are called conjunction, disjunction, negation. You can see the symbols and truth tables of these operations in this slide. Truth table. What is a truth table? Truth table is a table showing the truth or value of one or more compound propositions. This table is usually used for testing the validity of arguments. Besides two main operations, there are secondary operations which are built from the main operations. Examples are material implication and XOR operation. Material implication of x and y is not a x or y, and XOR x and XOR of x and y is x or y and not a x or not a y. Please check the truth tables of material implication and XOR operations by yourself. And in this slide, we will review Boolean algebra axioms very briefly and quickly. You can pause the video and look at them if you cannot keep up with the video space. Identity. Identity for AND operation is 1 and for OR is 0. It means that if you AND any Boolean variable or value with 1, the result will be that variable or value. Annihilator. Annihilator for AND is 0. It means if we AND anything with 0, the result will be 0. And annihilator for OR is 1, meaning that ORing any Boolean variable and value with 1 results in 1. Associativity. Associativity of AND operation and OR operation is same. It means that it doesn't matter in which order you AND or OR through Boolean variables. Commutativity. Commutativity of AND operation and OR operation says that it doesn't matter. X is OR to Y or Y is OR to X. Distributivity. Distributivity of AND over OR is shown below. The distributivity of OR over AND is the same and it's shown there. Idempotency. Idempotency of AND operation and OR operation says if you AND or OR a Boolean variable or value with itself, the result will be that variable or value itself. Absorption law, which is shown here, can be used in our minimization when we try to minimize equations or functions. Complementation law. It says ANDing a Boolean variable with its negated version results in 0. Also, it says ORing a Boolean variable with its negated version results in 1. Double negation. It says if we negate a Boolean variable for 2 times, the result will be the variable itself. De Morgan law. It says not a and b equals not a or not a b, and not a or b equals not a and not a b. Duality. It says that if an expression is valid, the dual of that is valid too, and it is obtained by interchanging the AND operations with OR operations and zeros with ones and vice versa. Note that you can prove all of these laws by using truth tables. And if any of these laws look strange to you and you don't have any intuition about them, just simply draw a truth table and play with zeros and ones until your understanding of them gets better. Logic gates. A logic gate is an idealized model of computation implementing a Boolean operation. They consist of transistors, electronic devices. They receive one or more binary inputs and send out single binary output. Inputs and output of logic gates are electrical voltages representing 2 values. High level shows 1 logic or true, low level shows 0 logic or false. This table lists logic gates with their symbols and the Boolean representation and the small description about them. Please pause the video and review the content. And in this page, you can find X or no, NAND, OR gates with their truth tables. Please pause the video and check them. Minimization of logic circuits. It is replacing one group of gates with another that will perform the same task for less number of gates, which the goals and benefits can be listed as being faster, consuming less energy and less transistors, and less area. And there are many mechanisms for minimization of logic circuits. Here we will check two mechanisms, Karnaugh map and QUINE-MCCLUSKEY. Karnaugh map, because of our pattern recognition capabilities as humans, is good for us. Besides, QUINE-MCCLUSKEY, which is functionally identical to Karnaugh map, is more efficient for using computer algorithms. Also, it is a more deterministic way to find the minimal form of a Boolean function. Before getting into Karnaugh map and QUINE-MCCLUSKEY, let's review some terminology together. Venn diagram is a diagram used for showing logical relations between sets, also used for illustrating simple set relationships in logic, also in computer science and etc. In the figures, as you can see, each closed curve represents a Boolean variable, and the red area shows the result of each operations on the variables. Sum of products, or SOP expression. It's a kind of Boolean algebra expression which in it the different product or ANDed inputs are being added together. Product of sums, or POS expression. It's another kind of Boolean algebra expression. In POS, the different odd inputs are being ANDed together. You can see the examples of each expression. Note that in expressing a Boolean function in SOP way from its truth table, the outputs 1 are considered, and in POS way, the output zeros are considered. Minterm. Minterm is a Boolean expression resulting in 1 for the output of a single row in a truth table, and zeros for all other rows in a truth table. And when we can say instead of row cell, when we mean cell in a Karnaugh map. And maxterm. Maxterm is a Boolean expression resulting in 1 for the output of a single row and 1s for all other rows in a truth table. You can see some examples with their truth tables here. Note that minterms and maxterms have their identified numbers. For example, they are known with their numbers. We say minterm number 0, M0, capitalized M1, maxterm number 1. Previously, we saw that Boolean functions are expressed in different ways, like algebraic expression, truth tables, POS, SOP, etc. Another way of expressing Boolean functions is showing them by sum of minterms or showing them by product of maxterms. Check these two examples here, that both of them represent a single Boolean function. Don't care conditions. What are these? In logic circuits design for some combinations of inputs, it doesn't matter what the output is. These outputs that are neither 1 nor 0 are called don't cares. We usually utilize them for further minimization. For example, we change them to 0 or 1 when we try to make larger rectangles in Karnaugh map, for example. Karnaugh map. We reviewed all those terminology to reach this point. Karnaugh maps are Venn diagrams. In fact, they are well organized to look neat. Two-variable Karnaugh map, in fact, is built by dividing the area by two variables into 4 regions, as shown in the figure. And the three-variable map, which can be found here, is built in the same way. For example, let's minimize this function. Let's minimize this function, which is expressed by sum of minterms. First of all, we draw the Karnaugh map with regard to the significance of variables and minterms and cell numbers. Then we fill our Karnaugh map. After that, we make rectangular groups containing total terms in power of 2, 1, 2, 4, etc. and try to cover as many elements in one group. In this example, we can cover all ones with 3 rectangles, as shown in the figure, and then we write those rectangles equivalent expressions. Here you can find another example with don't case. We said before that we utilize these conditions, these don't care conditions, to further minimize our Boolean functions or logic circuits. You will see as the number of variables increases in Boolean functions or logic circuits, that we want to minimize, working with Karnaugh maps gets harder and more time consuming, because we are going to make a lot of mistakes with relying on our pattern recognition capabilities. So we come to QUINE-MCCLUSKEY. This minimization method is also called the method of prime implicants. It is functionally identical to Karnaugh map, but it's more practical when minimizing Boolean functions with more than 5 variables. This algorithm involves 2 steps. In the first step, all prime implicants of the Boolean function is found. Then in the second step, those prime implicants that are used to find the essential prime implicants of the function, as well as other prime implicants that are necessary to cover the function. So let's review some other terminology. What's implicant? Implicant is a product term or min term in the SOP form of a Boolean function, or some term in the POS form of a Boolean function. For example, A and B and B and C, B and C are implicants here. And prime implicant. A prime implicant is a group of squares and rectangles made up of a bunch of adjacent min terms, which is allowed by the definition of Karnaugh map. For example, min terms 0 and 1 make a rectangle in a Boolean function only consisted of them. For example, just take it as example from me. Essential prime implicants. There are groups of min terms which cover at least one min term that it cannot be covered by any other prime implicant. Note that in the first step, when we try, in QUINE-MCCLUSKEY, when we try to find prime implicants, indeed we group min terms in the Karnaugh map. And we put min terms in a group which those are adjacent. In this table, in QUINE-MCCLUSKEY's tables, in the step 1, we do this when the binary number of min terms differs just in 1 bit. Then we keep this until there are no min terms. There are no more min terms that can be mixed together or grouped together based on their code distance. We will see this in our example. So let's see an example together. For example, we want to minimize the shown Boolean function. We need both min terms and don't case. Then we make groups of every two min terms that only differ in 1 bit. So we reach here, and then we put dash instead of that bit. We call them size 2 implicants, as it's clear here. Then we move towards size 4 implicants and repeat the same action until there are no groups to be mixed together. Note that if a group in previous subsection doesn't make group with other groups, we put it aside as a prime implicant. In this example, M4 and 12 is a prime implicant, and in the second step of QUINE-MCCLUSKEY, it should be considered. Finally, in the second step, we list the found prime implicants and the min terms they cover. We choose those that cover all of our function's min terms. Note that there might be more than one minimized form of our function, as this example shows it. Combinational circuits. These circuits are only made up of logic gates. The output of these circuits only depend on the levels of present inputs at any instant time. And these circuits don't use memory. It means that the previous state of inputs doesn't have any effect on the present state of the circuit. Well-known examples of these circuits are encoders, decoders, multiplexers, and demultiplexers. Decoder. It's a binary code to one-hot code converter. The schematic, truth table, and logic circuit of a 2 to 4 decoder is shown in this slide. Decoders are used as memory address decoding units and chip selectors and activators. Assume that this figure shows a memory which, based on the input address a row activates, which its data will be read or new data will be written to it. Decoder is used here to change a binary address to one hot code and select or activate a row of our memory. And in another example, let's assume that our 8 kilobytes memory has a banked structure, or in other words, it's partitioned or it's divided into 8 memory chips, which all of them are connected to the same address bus. A 3 to 8 decoder activates the right chip that data will be read from or written to. based on a path of our address. Multiplexers. Multiplexers also are known as data selectors. The schematic and the truth table of a 4-to-1 multiplexer is shown in this slide. You can see the detailed implementation of it with logic gates here. A good example of multiplexers usage in computer architecture is cache memories in CPUs. Coming data from different ways are selected based on the comparisons of tags ended with valid bits. Sequential circuits. Despite combinational circuits, these circuits have memory. In sequential circuits, the previous state of the inputs have impact on the outputs. Basic element that distinguish a combinational circuit from a sequential one is feedback. Latches and flip-flops are the essential elements of sequential circuits. Latch. What is a latch? Latches are asynchronous circuits. In these circuits, whenever input change, the output is impacted consequently. The usual story of latches begins with SR latch. And note that when you hear latch, you should remember sensitivity to level or triggered by level. The schematic of SR latch is shown in this slide here, and you can also see its truth table. And all of this truth table is going to work when E is 1, otherwise the Q is going to keep its previous state. And R and S cannot be 1 simultaneously, and it's a forbidden state. And when R is 0 and S is 1, the output is 1 and it's called its set. And when R is 1 and S is 0, the output is 0 and it's called its reset. The latch. It's an asynchronous circuit too that can be used to store 1 bit of information. The latch is used to capture or latch the logic level which is present on the D line, on the input line, when the E or control is high. When E is high and input D changes, then the output or Q follows the input. And when the input falls to 0, the last state of the D or our input is trapped and held in the latch. J call latch. It is similar to SR, but the difference is that we don't have forbidden combination of inputs here. And if we connect J and K in our J call latch, we will have a T or toggle latch. Flip-flop. What is flip-flop? What are flip-flops? Flip-flops are synchronous circuits. These logic circuits work with a global signal known as clock. These circuits output changes at the edge of the global signal or at the global clock signal. Flip-flops usually are built from latches. In the figure, you can see however the flip-flop is built from 2 D latches. Note that latches are called clock signal level sensitive or triggered, and flip-flops are called edge sensitive or edge triggered. This master slave flip-flop is negative edge triggered. It means that whenever clock falls from 1 to 0, the D input shows off in the Q output. Look at this waveform here and you will remember how it works. And synchronous sequential circuits can be categorized into 2 different groups, Mealy and Moore circuits. If you remember Mealy and Moore from automata theory course, you will get it easily and fast. From circuit schematic perspective, here in Moore machines or in Moore logic circuits, output values are determined only by its current state. However, in Mealy machine, output values are determined by its current state and by the values of its inputs. And from FSM or finite state machine view, for Moore machines FSMs, only inputs are placed on transition edges and all of output values are alongside the states. But for Mealy machines, input and outputs are on edges. This is because while an input in a Mealy machine changes, it can change the output instantaneously. But in a Moore machine, output changes only occur on global signals edges according to the current state and inputs values. Before getting into reviewing designing synchronous sequential circuits, let's review some terminology. State equation. It's an equation describing a clocked sequential circuit. It's a Boolean function specifying the next state as a function of present state and inputs. State table. This table shows the time sequence of inputs, outputs, and flip-flop states. We can consider it as truth tables. State diagram. In fact, state diagram is an FSM providing the same information as the state table shows. And when we design, we usually start with drawing FSM of our circuit. This figure shows an FSM. Then based on the FSM, we fill our state table as shown here. Then, after minimizations with the help of Karnaugh map, for example, we get state equations, and finally, we can have our logic circuit based on those equations. Let's see an example together. We want to build a logic circuit capable of detecting overlapping sequence of true ones. First of all, we design the FSM of this detector, which is a Mo FSM. Then we have to assign binary codes to the states or code our states to be able to be shown in our state table. Very important thing to remember here is that when we design with D flip-flops, we don't need to do anything to fill the state table. Simply, we use Karnaugh map on other minimization mechanisms or other minimization mechanisms to build our state equations, then draw the logic circuit. But when we want to use other flip-flops like T or JK, we should produce other columns listing flip-flops inputs according to the outputs, current state and next state based on the flip-flops truth tables. So let's get back to our example. After designing the FSM of our sequence detector, we fill our state table, and because we designed with D flip-flops, so we simply minimize with Karnaugh maps and obtain equations, and finally we have our logic circuit. And finally, the last topic that we cover in this video is changing flip-flops together. It can be very helpful. For example, assume that you have designed a logic circuit with D flip-flops, but in your laboratory, when you want to close your circuit, you have only JK flip-flops, and you don't have time to redesign you don't have time to redesign your circuit. So you can easily change JK flip-flops to D flip-flops. This slide shows how D and JK flip-flops can transform to each other. And this one is on the transformation of D to T and vice versa. And finally, this one is for JK and T flip-flops. In this video, we try to review what we should know about logic circuits on our journey to the computer architecture world. I emphasize that this video is for those who studied logic circuits earlier. And finally, thank you very much for your time and attention.